All right, let's get started. So today we're going to be talking about interference, which we've kind of introduced previously, but there's a lot of phenomena related to an interference that we need to talk about. So that's going to include things like two-source interference, diffraction, um, functional things like thin film interference, and interferometers, which is a way that we measure really tiny distances. Um, and so we have a lot of kind of applications of the same principle to go through, but we're going to keep coming back to the kind of basics of constructive and destructive interference and just come up with some ways of explaining particular cases and particular situations. So one of the applications of interference that is just really relevant to physics at UW-Bothell in particular is related to gravitational waves. So you may have heard people talk about gravitational waves. We have a couple of faculty members who study gravitational waves. One of the apparatuses that measures the gravitational waves is located in Washington State. So the idea is that there are these they're called quadrupole waves created by um, accelerating objects in space. So for things like two black holes accelerating around one another, creates these, I say quadrupole waves because they don't look like sine waves, like crests and troughs, the way we've been visualizing them. Those would be what we call dipole waves. You can draw them with like an arrow that's like pointing up or down. These quadrupole waves are kind of like circles that get stretched into ovals one way or the other. Um, and so what these waves do is they distort space-time such that a circle becomes, like if I were to draw a circle on the ground, it would get stretched out to become an oval. Uh, Understandably, the amount of stretching that happens here is really, really small. So to actually detect gravitational waves, you have to be able to measure ridiculously tiny distances. And so the way you measure really tiny distances is with an interferometer. So the reason interference is really useful for measuring really small distances is that you're basically using two lasers and arriving at constructive or destructive interference based on the distances those lasers have had to travel. So your precision becomes on the same order as the wavelength of the light that you're using. So now I can detect changes corresponding to like two crests lining up versus a crest and a trough lining up. So if my wavelength is in the nanometers, now all of a sudden I have a way of measuring nanometers, which is otherwise quite difficult to do with something like a ruler. So the way we measure gravitational waves is with a giant interferometer that's basically just a laser that gets split along two paths. And these paths are, over 1 kilometer long, and the laser just goes down to one end, bounces back, and then you just see whether the two lasers interfere constructively or destructively. So using an interferometer, basically I need to use a laser because I need my light to be coherent so that all the light coming out of the laser, is all coming out with crests at the same moment. I need a beam splitter, which is a way of dividing the same light along two paths. So typically this is like a half mirror or a mirror that only reflects half the light that hits it while the other half passes through. And then I have two arms. And so the arms are just the laser traveling from the beam splitter out to a mirror and then back to the beam splitter. Then I take the light that comes back and send it to some sort of detector, right? We can kind of visualize it as a screen where I see if I have bright light or no light, which tells me whether I have constructive or destructive interference. So we know from last week that the constructive or destructive interference is determined by the path difference. So we have to keep track of the extra amount one of these two waves has traveled. If they've traveled a different distance, then one crest might be lagging behind the other, and it depends by how much if we want to figure out whether we have constructive or destructive interference. So in the case of an interferometer, if I call the lengths of each arm L1 and L2, I care about the difference in those two values to find the path difference, and I need to double it because my light makes the journey out and makes the journey back. So if I start in a situation where I have destructive interference, where the light coming from the two different pathways lines up crest to trough, then that means the path difference I have is going to be something like lambda over 2, or 3 lambda over 2, or 5 lambda over 2, or something similar to that. So if I lengthen one of the arms, when the screen becomes bright, I know that the path difference has now changed to a whole amount of wavelengths. So now I've gone from lambda over 2 to lambda. If I keep lengthening the path such that the screen becomes dark again, that means now the path difference has grown to the next half integer multiple of lambda. So if I start out dark and I go bright, then dark, then bright again, I've gone from a path difference of something like lambda over 2 to a path difference of something like 2 lambda. So that's a difference of 3 lambda over 2. So 3/2 the wavelength gives me the amount the path, or gives me the amount the one light has gone on a longer journey. But I also, right, have this factor of 2 where, right, lengthening the arm, the path difference is double whatever I change the length of the arm by. So I don't just have to take 3/2 of the wavelength, right? Then I have to divide that by 2. So I arrive at 487.5 nanometers is the amount that I've moved one of these mirrors. So this is really cool because it would otherwise be quite hard to measure a distance like 487.5 nanometers, right? There aren't a lot of really easy to use tools that can measure distance that precisely. So that's the real benefit of using an interferometer and why they're kind of interesting and relevant in modern physics experiments. Okay. So this is the same kind of thing, just kind of written out, maybe a little bit cleaner. So, right, I go from dark to bright to dark to bright. So I go from lambda over 2 to 2 lambda. Path changes by 3 lambda over 2. Cut that in half. So my difference in length is 3 lambda over 4. Okay, so interferometers are really cool. They're also pretty far removed from interference we might do, or we might see in real life. So, or in everyday life. So I want to look at just 2 sources of, say, water waves on the surface of the water and identify what patterns we can find in terms of where we have constructive and destructive interference. So if I want to flag spots where I have constructive interference, right, I'm looking for spots where a crest lines up with a crest or a trough lines up with a trough. If I'm looking for destructive interference, that's where a crest lines up with a trough. So this way of visualizing it, I've got 2 sources here, and they're producing waves. The waves are radiating outward from these sources. And so I can follow the crests as they move outward radially from these 2 sources. So if I have a spot that's undergoing constructive interference, right, where there's a crest and a crest lining up to one another, I want to think about what happens at that point as time goes by. So what I can do is I can trace the motion of the trough, right, radially outward. And if I imagine letting this go, this trough is going to arrive at this green point, this trough is going to arrive at this green point, and so sometime later I'll have 2 troughs lining up with one another. So another way to put that is places where I have constructive interference will continue to have constructive interference. So there are just locations where I'm always going to have constructive interference and other locations where I'm always going to have destructive interference. If I were to plot out, right, some of these points, right, I could see that I can keep track of that path difference. So say this point where I've got destructive interference is a distance of 3 lambda from one source. So 1, 2, 3 lambda from that source, and a distance of 1, 2, 3.5 lambda from the other. So that means there's a path difference there of 0.5 lambda. So I know that half lambda is going to give me destructive interference, so this isn't super surprising, but it's nice to be able to see this on a visual, right? It's nice to be able to just count out the wavelengths from each source and see that I do in fact have constructive or destructive interference when I have the right sort of path difference. So any point that I find that has destructive interference should have a half integer multiple of lambda in terms of their path difference. So I should be getting half lambda or 3/2 lambda for any point on this image that I find destructive interference. And I can go through those points, and I find something interesting, which is that if I map out all the points that look like destructive interference, they sit along straight lines. So I can identify an entire straight line of points where I have destructive interference. And furthermore, I can say that actually every point on this path has half a wavelength path difference. So, right, this was the point we looked at before. If I look here, that's 1.5 from the source on the left and 2 from the source on the left, 1.5 from the source on the right. So every point on that line has a path difference of lambda over 2. Meanwhile, over here, every point on this line has a path difference of 3 lambda over 2. Right? There's an extra lambda and then a half between these two sources. So along the line connecting them, they're going to have a path difference of 3 lambda over 2. I can do the same thing for constructive interference, right? I can find lines where every point along that line has a path difference of 0, and I can find a line where every point on that line has a path difference of lambda. If I look at this picture, right, I don't actually see any points that have a path difference of 2 lambda. And there's very good reason for that, which is in this example that I've drawn here, the two sources are separated by a distance of 3 lambda over 2. There's no way that I can get a path difference bigger than 3 lambda over 2. There's no point in space where one of the two waves will have had to journey an extra 2 full wavelengths, right? So there's only, the biggest path difference I could have is along this line here, where, right, I'm along the line connecting the two sources, and whichever source is in the back, that wave is going to travel an extra 3 lambda over 2. That's my biggest path difference I could have. So there's only going to be a certain number of these points with constructive and destructive interference. I don't carry on to infinitely large multiples of lambda because I'm just strictly limited by the spacing between the two sources. So the fact that I can draw this picture kind of motivates me to try to, rather than have to draw this picture every time, try to just identify what are some angles that I can calculate where I know that those angles are going to let me draw lines that always give me constructive or destructive interference. And I can boil down the problem of two-source interference to just finding these angles. So we already kind of talked about that. So I can kind of zoom in to what's happening here with my two sources. I can make some approximations. So I can imagine that the two sources are much closer together than they are compared to the distance to me. So if I'm receiving the wave, I'm much further away from the two sources compared to how close together they are. So this big distance d is much bigger than my little distance d between the two sources. If I do that, then I can approximate the path from the source to me as two parallel lines, right? I know these two lines would converge at me, but if I'm really, really far away, these two lines are basically parallel. If these two lines are parallel, I can think about drawing basically a right triangle here in order to calculate the path difference in terms of the angle. And so that's what I want. I want to identify what angles are going to give me constructive and destructive interference. So if I draw that right triangle, the equation I get is that the path difference is going to be given by the distance between the two sources times the sine of the angle. And so that angle being measured from the normal, right? The normal that goes straight away perpendicular to the surface, right? I measure the angle to the line that's pointing at the receiver, and then I can use d sine theta, where d is the distance between the two sources, to find the path difference. So this is really useful because, right, for this path difference, I know that this path difference has to be lambda over 2 or 3 lambda over 2 or so on for destructive interference. And I know it has to be lambda, 2 lambda, right, or so on for constructive interference. So this will let me figure out what angles are always going to correspond to constructive or destructive interference, which simplifies the problem out a lot for me because now I don't have to draw a big picture and map out all those points. So the example we had was a laser through 2 pinholes onto a screen, the screen being 2 meters away. So right away we can see that the distance to the screen is much bigger than the separation between the two holes. So I can use my equation pretty confidently. I made the equation semicircular, so we wouldn't have to worry about the fact that like, any kind of strange geometry to a flat screen, right? So I only have to really worry about the angles. And I know that, right, every light and dark spot will show up on the screen. Like there's no edge of the screen that I've got to worry about or anything weird happening like that. So I can use the equation I just figured out to find the angles that give me bright spots and dark spots. So for bright spots, I'm looking for a path difference that corresponds to either 0, lambda, or 2 lambda. And I'm going to use, right, delta x equals d sine theta. So the angles I find for theta equals 0, well, that gives me a path difference of 0. I get theta is 22 degrees for a path difference of lambda, 49 degrees for a path difference of 2 lambda. And if I try to plug in 3 lambda, which would be the next point of constructive interference, I have a problem because that gives me 1350 over 1200, which is greater than 1. And there's nothing I can plug in terms of angle where sine theta is going to be greater than 1, right? There's no way I can get that. So there is no angle that gives me a path difference of 3 lambda. So in terms of what angles I've got 3 angles that give me constructive interference, and I don't have to worry about any path differences bigger than 2 lambda. If I do the same thing for dark spots, right, then I plug into the same equation, but now my delta x is lambda over 2, 3 lambda over 2, 5 lambda over 2, and I can quickly put together this map of what the screen is going to look like. So if I actually look at the screen, I'm going to see an alternating array of bright and dark spots, with bright spots corresponding to the angles that give me the path differences of 0 lambda and 2 lambda, dark spots in between corresponding to path differences of lambda over 2, 3 lambda over 2, 5 lambda over 2. And I know I've got the central bright spot, and then on each side I've got 2 more, and then that's it. I don't have a third bright spot to the right of my last dark spot because that path difference was too big. Okay, so if I were to instead look at a flat screen, right, and maybe do this whole process backwards, then I could find the distance, right, between the 2 slits, knowing the angle that gives me the bright spot. So in this case, I'm given that the distance on the screen is 50 centimeters. So the first thing I'm going to have to do is find this angle, right? Because the equation I've got tells me about the path difference and the separation between the slits, right? D being the separation between the slits being the thing I really want to find. That is figured out in terms of angle. So I need to calculate the angle, which I can do knowing how far away the screen is and how far away the 2 bright spots are. So, right, I could do that, right, with tangent of theta is going to be 50 centimeters over the distance to the screen, right? That could give me the angle. I know the wavelength of the light, and so from there I could figure out D. Now, if the wavelength was changed, right, then something about the pattern on the screen is going to change. So, for example, with this d sine theta, if the distance between the slits is not changing, right, as I decrease the wavelength. So if I decrease the wavelength, the only thing that can change is sine theta, meaning that my angles are going to get smaller. So if I use a smaller wavelength, so that would be, right, light that was, say, more blue or more purple, right, higher frequency, shorter wavelength, then those bright spots would get closer together. Okay, so I just kind of want to engage in a little bit of thought about what would happen if I had a third slit opened up, right? And the reasoning for this is going to lead us to a discussion about diffraction gratings. So the idea here is if I open up a second slit, right, then I have to ask, is the light from that extra slit going to interfere constructively or destructively with the light from the first 2? So, right, to figure that out for 2 sources, I found this little delta x here and asked whether that delta x was lambda, 2 lambda, or a half integer of lambda. If I have a third slit, right, I could draw this triangle again, and I could look at a situation where slits 1 and 2 have constructive interference. So if, say, delta x is equal to lambda, that means my first two slits are undergoing constructive interference, and my second two slits are also undergoing constructive interference. Okay, so what does this tell me? This tells me that if I open up the third slit, then spots that were bright are still going to be bright. I still have constructive interference because I still have a whole integer multiple of wavelength as a path difference. However, if I look at the dark spots had a delta x of lambda over 2, but now slits 1 and 3 have double that path difference, which would be lambda. So that means slits 1 and 3 are now interfering constructively. So this isn't a dark spot anymore. It's not going to be a maximum because slit 2 is still not cooperating, but my dark spots are not still going to be dark spots. My bright spots are still bright spots, but now I've got something more complicated happening between the two bright spots. I can kind of try to see how this trend goes. If I have 4 slits now, right, my argument about bright spots should still be bright spots, right? If 2 neighboring pairs are interfering constructively, then all 4 should be interfering constructively. Now I have a dark spot. Let's see, I've got a dark spot where delta x is lambda over 2. Yeah, because now slits 1 and 2 will cancel out, and slits 3 and 4 will cancel out. But now I've also got more dark spots, right? At lambda over 4, now, right, this distance between, or the path difference between slits 1 and 3 will be lambda over 2. So now slits 1 and 3 will cancel out, slits 2 and 4 will cancel out, and then I've got a dark spot. I'm also going to have one at 3 lambda over 4. So as I'm cutting slits, my bright spots are staying the same, but my dark spots are multiplying. I'm now having more and more locations where I've got destructive interference. So this is a way of kind of working up to explain a diffraction grating. So diffraction grating is basically a material where I'm going to poke holes at precise spacing, but I'm going to poke loads and loads of holes throughout the material. So the whole material is made up of slits, and I'm going to have lots and lots and lots of different slits, right? Lots and lots of different sources, all interfering with one another. These are often described in the lab in terms of lines per millimeter. So they'll talk about the number of holes that have been poked in per millimeter. It's like the number of slits cut per distance. And you could get, hundreds of lines per millimeter if you want. So this actually has the same equation for bright spots as we had from two-source interference, right? The same bright spots that we were talking about just for two-source interference, but now there are lots of dark spots. So why is something like this useful? If I look at the pattern that's going to show up on the screen, right, compare two-source interference to the diffraction grating, the two-source interference is going to be smoothly changing from constructive to destructive interference, and so it's going to have these broad bright spots and broad dark spots. The diffraction grating is going to have these really narrow bright spots separated by large distances. So this is actually a really useful way in an experiment to separate out different wavelengths of light. So for instance, whatever wavelength I'm using here is bright at a very specific angle, and it's a very narrow bright spot. So if I were to use a different wavelength that had a bright spot that was at a different angle, those would be sufficiently well defined and sufficiently far apart that I'd be able to actually pick out one wavelength or the other. So this is a way of separating out the different pieces of light and changing out like wavelengths. So if I have a spectrometer, say, and I want to measure the amount of each wavelength of light that I have, this would be a critical part of that instrument. So for practice, we consider a grating with 200 lines per millimeter. So that means the distance between two neighboring slits is 1/200th of a millimeter. I'm going to use yellow light with a given wavelength, and I'm going to shine that onto a flat screen. I want to figure out how far apart these two maxima are on the screen. So if I do that, I can use the same equation I had before to find the angle. So the distance is 1/200th of a millimeter, so 10 to the 3 meters over 200. the wavelength, right, was 570 nanometers. So I can find an angle of 6.5 degrees. And I can figure out where on the screen that shows up. So the reason why, like I said, this is interesting is if I were to say use 400 nanometer light instead, that would result in a smaller angle. If I was to use 650 nanometer light instead, that would result in a bigger angle. So if I actually look at the screen, I can see very distinct green, yellow, and red spots on the screen that are separated out from one another. So if I needed to, say, measure the amount of green light versus red light that I have, this would be how I could do it. Okay, so the next kind of system we're looking at is diffraction. And this is not to be confused with what I was just talking about, which is diffraction gratings. I know, needlessly confusing. A diffraction grating is really talking about interference between multiple sources. Diffraction is something totally different. Actually, diffraction and diffraction gratings have much less in common than diffraction gratings have with interference. So I don't know why they're not called interference gratings, but they're not. They're called diffraction gratings. Diffraction is a separate phenomenon. So diffraction is this idea that a wave will deform and bend around corners if it's put through a finite sized hole. So if the width of the slit is on the same order as the wavelength, then I'm going to have bent wavefronts where the wave is going to spread out around corners. I'm also going to arrive at certain angles that will give me dark spots. So if I put the pattern on the screen, we can see it doesn't really look like either of the two patterns we were looking at before. There's this broad central maximum with minima on either side, and then smaller, less well-defined peaks going further outward. If you have an electrical engineering bent, this shape is the Fourier transform of a square wave, which is kind of cool. Basically, you're taking the Fourier transform of the shape of the slit. If you don't know what that means, that's fine. It's just kind of a cool fun fact for those who are going to be EEs. And so the equation we're going to arrive at looks similar to the equation we had before, but there's some key differences here. Specifically, right, W is now referring to the width of the slit rather than the distance between two slits. And even though this looks like the equation we had for bright spots, it is now the equation we have for these dark spots. So that's really easy to get confused on. And in fact, through this unit, we have a ton of equations that look similar but mean slightly different things. So it's important to double check that. So this is what an actual diffraction pattern looks like if I'm shining light through a slit. This would be the pattern I see on the screen. You can see these really sharply defined minima there. And if I make the slit narrower, right, then I'm making the width smaller, keeping the wavelength the same. So that means sine theta has to be getting larger. So if I make the slit smaller, then these minima are going to get further apart. So the kind of limiting factor we can think about here is if I made the slit really wide, then it would be just kind of like shining a flashlight in a hallway, right? The beam would kind of pass straight through, nothing would bend, I just have a spot of light the same size as my flashlight beam. If I make the slit very, very small, then it behaves like a point source, right? The light is now spread out evenly throughout all the different angles, right? And it looks like a point source of light and there's no dark spots at all. If I am somewhere in between though, this is when I get those somewhat complicated interference or complicated diffraction patterns where I have this broad maximum and these angles that give me a dark spot. So I need a width bigger than, but still kind of comparable to the wavelength to see this effect. And it's not critical that we know how to do this, but the way we kind of derive this equation is by pretending that my slit is actually a ton of tiny little point sources all providing light. And so this goes back to like Huygens principle and modeling, right, how light moves through space. But to find the angles that give me destructive interference, I have to find angles where these sources all cancel each other out. And so the first such angle would be if I paired all of these sources up with one another into little pairs that cancel each other out. And so I had an infinite number of pairs of slits all canceling each other out. These two pairs would be separated by half the width of the slit. So this is how I get my equation, right? I have my two sources separated by width over 2 give me destructive interference. And so when I cancel out the 2's, I end up with an equation that looks like the equation we had for constructive interference, but is actually the equation for destructive interference in terms of this diffraction slit. So like I said, tricky, but make sure you're using the right equation. So the book gets into the famous double slit experiment, which is the idea if I shine light through 2 slits, I'm going to get an interesting looking pattern on the screen. And the reason why this is interesting is because I have to simultaneously cope with the interference between the 2 slits, but also the fact that these 2 slits have finite width, and therefore I'm going to see diffraction as well. So I'm going to see dark spots from diffraction, and I'm going to see bright and dark spots from interference. Thankfully, visually, this is pretty easy to sort out. So if I have single slit diffraction, right, I have this point where, or have this shape where I have this kind of broad peak with these, right, dark spots on either side. If I add a second slit, right, I can figure out what angle is going to give me destructive interference, and I'm going to find out it's going to be a much smaller angle for the interference dark spots. So that means my interference dark spots are going to be spaced a lot more tightly together than my diffraction ones. So I can think about the diffraction as this broad shape here, and I can think about the interference as causing these fine structure minima and maxima. So in this picture, C, D, and E all correspond to interference between the 2 sources, whereas A and B are the minima caused by this large scale shape. These are being caused by diffraction. So I could just use the 2 equations and plug in the distances between the slits in case of interference, or plug in the width of the slits for the case of diffraction and get the right answer. But it's useful to have this kind of visual intuition to like understand from the pattern on the screen, like which of these minima are caused by interference and which are caused by diffraction. Another way of asking this would be to talk about, okay, if I decrease the width of the slit, then I'm impacting this overall shape that I've got here. I'm not impacting the kind of fine structure of little ups and downs inside that shape. So decreasing the width of the slits is going to broaden out that central pattern. And so that would be the equivalent of going from, say, like case 1 to case 3, right? My large, wider shape is getting wider going from case 1 to case 3. Meanwhile, if I change the distance between the 2 slits, then I am affecting the interference. So now I'm keeping the same shape overall, but now I have a lot more of these spacing, a lot more of these, a different amount of these little pluses, these positives and negatives inside my broad shape. So if the distance between the 2 slits is decreasing, then my bright spots and dark spots due to interference are going to get further apart, right? They're going to move to larger angles. So that would be the transition from case 4 to case 2. So I'm not affecting the width, so I'm not affecting the overall shape, but I am changing the angle that gives me these little fine structure minima in here. So I'm going from a smaller to a larger angle for the interference. So I'm going from case 4 to case 2. Okay, so we've talked about like kind of 2 source interference and interferometers. We've talked about diffraction gratings, which are what happens when I have interference from lots of different sources. We've talked about diffraction, so the pattern that shows up from the finite width of a slit. And we've talked about Young's experiment where the 2 of these things show up at the same time. So the last case I want to look at today is probably the most complicated, and that's related to thin film interference. So this shows up if I want to make something like an anti-glare coating, right, where I want wavelengths to not be brightly reflected off of a surface because I don't want glare. It also shows up if I say look at a thin coating of oil on a puddle. It looks colorful. And the reason for that is that certain wavelengths of light are reflected brighter than others due to this phenomenon. And the colors change, and you can actually calculate the thickness of the film of oil from what color it is, which is kind of cool. So the first thing that we need to remember, and it seems weird that we need to remember this at this moment, but the first thing we need to remember are which of the cases give us upside down reflections. And so this was when we were playing with a string, right? The idea was that if a wave came on a light string and reflected off a heavy string, that was like reflecting off of a fixed end, and so it came back upside down. Whereas if a wave came in on a heavy string to a light string, it was reflected right side up. So now we're talking about light waves rather than strings. So rather than talking about the weight of the string, we're talking about an index of refraction. So going from a fast string to a slow string is saying that the second string has a larger index of refraction, whereas going from a slow string to a fast string is saying that the second region has a lower index of refraction. So we're going to have an analogy for this wave coming back right side up or upside down. And it's going to follow along with this intuition of how fast the wave is going in a different medium. So if a wave comes in a fast medium and reflects off a slower medium, it's going to come back upside down. So that means the reflected wave is going to get a pi phase shift. Whereas in the case where I'm reflecting off of a medium that has a lower index of refraction, there's no such phase shift. And this is going to be important because whether my wave is coming back right side up or upside down is going to determine whether there's a crest or a trough. And that's critical to figure out whether I've got constructive or destructive interference, right? If I was going to line up a crest with a trough, but then I flipped one of them upside down, now I've got a crest and a crest, and all of a sudden I've got constructive interference instead. Okay, so quick review for index of refraction, right? We can figure out that the speed of light is being determined by mu naught and epsilon naught, but the speed of light in mediums that have some reaction with the electric or magnetic fields is going to be slower. They're going to have different mu and epsilon values. They're going to be slightly polarizable or slightly magnetic or things like that. And so in material, light could be traveling slower than the speed that we know and love. So in the vacuum or in air, it's traveling at pretty much the speed of light. It is traveling slightly slower in air than in the vacuum, but it's very, very minor, and so we typically don't worry about that. However, light does travel significantly slower in water and glass and plastics and other transparent solids. So those have indices of refraction that are significantly different to 1. So if I have light, like I said, coming in from a faster medium to a slower medium, right, that wave is going to reflect upside down. The other thing I have to worry about is when the wave slows down, right, then the spacing between two crests is going to change. So this was like when we had those two pulses on a string going from a faster to a slower medium, right, they got squished together when they slowed down. So just like we had before, the timing between two crests doesn't change. And so what that means is that the frequency is going to stay the same from one medium to the other. The wavelength, however, is going to change. Specifically, if the wave slows down, the wavelength is going to get shorter. If the wave speeds up, the wavelength is going to get longer. So when we're talking about waves traveling in other mediums, we care about the wavelength in that medium, right? Whether the amount of phase that happens when a wave travels through a medium depends on how many wavelengths it went through in that material, right? And so that's going to be something we have to keep track of. Okay, so with those two connections made, now we can talk about thin film interference properly. So the idea behind thin film interference is that the two waves that are interfering with one another are the wave that reflects off the top of the thin film and the wave that reflects off the bottom. So I always draw this picture to this day in order to keep track of the different things at play here, right? There's a lot of different things happening at the same time. This is the sort of problem you definitely want to take some time out to organize your thoughts. So we're looking at the wave that reflects off the top of the soap film, in this case, and the bottom of the soap film. We don't worry about the wave that travels into the thick layer, like glass, because by the time that wave gets back up, it's no longer going to be coherent with waves 1 and 2, right? It's no longer going to have all its crests and troughs lined up with the light that's participating in 1 and 2. So we don't worry about the wave that goes on a longer journey, right, interfering with 1 and 2. So we only ever have 2 waves that we're worried about, just the one off the top of the film, the one off the bottom of the film. So to figure out whether these interfere constructively or destructively, I need to figure out, right, what is the difference in phase? If these are pi out of phase, that means they're now going to be interfering destructively. If they're in phase or 2 pi out of phase or 4 pi, right, then I know they're going to be basically lined back up and interfering constructively. The problem or the challenge with finding the phase is that there's a lot of different things happening. So I have to keep track of, right, the reflections, whether or not I have those phase shifts, and I have to keep track of the path difference that the second ray has traveled through the film. So because there's several things to keep track of, this is the way I recommend actually handling this problem, writing down the phase that each of the 2 waves experiences. So the first wave reflects off the top of the soap film. So it gets a phase shift, right? It gets a pi phase shift because it reflects off of a higher index of refraction. So it comes back upside down. Now, wave 2 does not get that pi phase shift. It is reflected right side up because it's traveling in the soap when it bounces off the glass. So it's traveling through a medium with a high index of refraction, reflecting off a medium with a low index of refraction. So it does not get flipped over when it reflects. However, wave 2 does travel an extra distance. So wave 2 is going to experience a phase shift from traveling extra distance compared to wave 1. So our expression for phase in terms of path difference was the extra path traveled over the wavelength times 2 pi. The extra path traveled, that's kind of easy. That's just twice the thickness of the film, right? It goes down into the film and back out. The wavelength, though, is going to be the wavelength in the soap. So I actually, if I want to express that in terms of the wavelength in air, which is probably the one that I know, then I have to divide it by the index of refraction of the soap. So that's why I get the index of refraction of the soap here, because I have to correct the wavelength, because the wavelength is different in the soap. So when I put this together, now I can find the phase shift of wave number 1, the phase shift of wave number 2, and the difference between those 2 phases will tell me whether I have constructive or destructive interference. So I can take the difference between these 2. I don't have to worry about theta 1 minus theta 2 versus theta 2 minus theta 1. I can take whichever because I don't really care which wave is ahead or behind of the other. I just care about kind of the absolute value of that phase shift. So if that phase difference here that I wrote down is 0, 2 pi, 4 pi, what have you, then I have constructive interference. If it's an odd multiple of pi, then I have destructive interference. I do not want to memorize this equation and write it down because this is very situational, right? I don't know whether I'm always going to have this pi up here. I don't know whether I'm always going to have this pi or not have this pi down here, right? This equation could be different for different films on different situations. So this equation for delta theta is not always the answer, right? I have to actually go through these steps of identifying all the different phase shifts that are happening if I want to get the right answer. So for example, if I had a film of plastic on a metal, right, then I would actually have phase shifts on both of these reflections. So both wave 1 and wave 2 in this case would get that pi phase shift. So if I used that same equation I just figured out, in this situation, I would get the wrong answer. Okay, so now if I'm looking at a film of plastic on metal, right, then I have the phase shift in both of those two situations, meaning that when I take the difference in phase, those two pi's cancel out, and I end up with a different expression for my phase difference. If I want to talk about what wavelengths are going to be reflected brightly, then I need to look at constructive interference. If I want to talk about what wavelengths are not going to be reflected off this metal, then I'm talking about destructive interference. So if I know the thickness of the film and the index of refraction, and I've gone through my careful analysis up here, then all I need to do is set that phase difference equal to different values of pi, 3 pi, or 5 pi, and that will identify some wavelengths for me that are undergoing destructive interference. There's an infinite number of wavelengths. Typically, we just want the first 2 or 3. We're especially interested in ones between like 100 and 1,000 nanometers because those are like visible light. So if we're talking about anti-glare coatings, I am most interested in those wavelengths. But typically, if I ask you to find some, finding 2 or 3 is sufficient. Okay, so if I look at the problem where I'm looking at a film of oil on top of glass, and I shine light on the material, in this case, I know that red light comes back bright. So this is the same kind of problem, but instead of knowing the thickness of the material, I now see that the film looks red. So this is actually reflective of something you could do in real life. If you see oil on the ground on a rainy day, it will look colorful, and you can actually calculate the thickness of a film from the color. So let's work through that phase discussion here. If I have oil and glass, then the wave that reflects off the top of the oil gets that pi phase shift. The wave that reflects off of the glass does not. And instead, all I have to do is give that 2 pi times the difference in path, so twice the thickness, divided by the wavelength. But of course, the wavelength also depends on the index of refraction of the glass. So I arrive at a phase difference equation that looks like 4 pi times the index of refraction of the, sorry, not the glass, but the oil rather. Index of refraction of the film times the thickness over the wavelength. So in this case, we know that 650 nanometers reflected brightly minus pi. And so if that's coming back brightly, then I have a situation where I have constructive interference. If I'm looking for the thinnest film, then I should probably go for the smallest value here, right, which would be a phase difference of 0. And if I plug in a phase difference of 0, that gives me a thickness of 101.6 nanometers in this expression. Once I know the thickness of the film, I could find other wavelengths that come back bright or come back dark. All I have to do is plug in for thickness and set the phase equal to, right, some even multiple of pi for constructive interference or an odd multiple of pi for destructive interference. Okay, so that's a lot of different situations, but we are in fact done talking about different interference phenomena. Like I said, the thin film one, there's a lot of different things happening conceptually, so I would just really take your time and err on the side of writing stuff down rather than trying to kind of jump to the right answer. Okay, so that's what I need to say about these kind of interference phenomena. Let me know if you have any questions or anything you would like me to talk about.